So going to talk about the problem. We're going to talk about the solution on Google Cloud specifically. Go into the solution architecture of what it actually looks like, the nuts and bolts of the solution. And then we'll talk about the technical and the business highlights of the solution and why you should care. Current state of affairs, right? I work at Deloitte, and we have the opportunity to work with many of the Fortune 500 companies. And I'm on the Google Cloud side and on the technical side. So I see firsthand these problems present themselves across the board. No one's exempt. So what we've noticed in doing many of these deployments, right? So all companies right now, Kubernetes is the hot word, microservices, moving to a containerized architecture. There's definitely a lot of benefits around that in and of itself. Fast time to market, fast time to change, redundancy, scale, all those things, the hot items, right? So everybody wants it. They also, if you've moved in that direction, you have a lot of developers probably pushing you in that direction. And so those developers want a platform that can help them deploy their services. So that's a self-service platform that is almost required. And you hear a lot of platform engineering. This is the buzzword these days, and that's exactly what they're asking for, is a self-service platform for them to deploy services on any cloud. And they also want that automated. And what does that look like? So when you make a pull request, a merge request of your code back into the master, as a developer, all you want to care about is your code, your application code. And from there on, it should be an automated process in checking it in running it through some tooling, validation checks, that kind of stuff, as well as it may build a container with your code and update it and then deploy it to production or to an environment of your choosing. So that's the automation piece. So in the real world, when this happens, right, how do you go about building all of this, all the things that developers want, all the things that developers need, right? When you end up doing this, it becomes complex. It is a complex thing by nature. And so you also move into your Kubernetes cluster, and how are you going to expose those developer applications to the outside world? The industry standard for a long time has been Kubernetes ingress. Ingress is simply a YAML file on Kubernetes, and when you apply it to the cluster, it tells the cluster to, underneath the hood, make a node port, but it tells the cloud provider to build a load balancer to send the traffic to those node ports. So you get a lot of things when you deploy a single file. And you get a load balancer outside the cluster. Your outside users can hit services inside the cluster. This has been the industry standard for a long time. And what has happened is all of these companies, your F5s, your Nginxs, et cetera, have made proprietary ingress so that they can maybe integrate features of their own product. So like F5, they have an ingress, and it incorporates a WAF inside the ingress. So you can see why it's valuable and it's important, and people have gone that way. But what happens when you deploy the F5 or the Nginx ingress? You're locked in. It's proprietary. There's not like you're dependent on that vendor at that point. So ingress in itself has some issues. There's also an issue of separation of duties, security perspective. So an ingress is, like I said, a single file. Where does it sit inside the cluster? Does it sit in the security namespace for the security team to administer? Does it sit in the platform namespace, so like infrastructure could administer it? Or the developers are going to need to make changes to it all the time, so the developers want access to it. So you have this shared file, but yet it controls the traffic coming in and out of the cluster for all of the applications. you can see the problem there, that this single file and it becomes, a big deal. So it has its own issues, right? So, and that's where we're getting at mixed shared responsibilities, right, for developers, platform, and security. Who's going to own it? This is always a fight. It's not a fight, it's a heated discussion. It always is a problem, though. So what happens if the wrong team ends up owning it, right? So what happens when security gets pointed at to own the ingress? That means there's an upskill factor, right? So your security team has to learn Kubernetes, learn ingress, learn all the facets of the YAML and deployment, right? Platform team, it makes sense, but then platform team gets run down because developers have a lot of requests. And then the developers, let's just say a standard app might have 20 microservices in it, and they all want references in paths to be defined in the ingress. It can become cumbersome for the platform team to own. And then if we hand it to developers, developers have the keys to the kingdom. And we want them focused on code. They also have an upskill for learning ingress, but we might not want them to expose services outside the cluster haphazardly. And developers like to deploy, not secure. So all the teams have their own problems, right? So in this, and if you have to host meetings to discuss it, to work through it, to get everybody, the security platform and the developers all on the same phone call, it's a costly phone call, it takes time, and then you get management complaining about the sluggishness of the deployment. So we just focused here, just some bland pictures, but you can see the ingress here in this lower diagram, that exactly what we're talking about, right? So if you have domain.com, maybe you have foo.domain.com or my domain / something. All these paths have to be defined in the ingress, and all those paths have to point to a service. So you could see configuring all this, it's going to be somebody's job. So this slide is particularly looking at and putting under the microscope what's happening when this takes place. So if you're putting all the impetus on the developers, right, in this first graph, the developer responsibility increases a lot. They have to learn Kubernetes, they have to learn cloud, they have to learn ingress, they have to learn many things. They're responsible for many things. So this puts a lot of pressure on developers, and then it leads to quicker burnout, right? So the way that the industry's been moving is this platform as a service, right? So I have this platform, and if I enable self-service and enough control and enough flexibility that the developers can just use and move themselves, not involving any of the platform, and they can deploy in a safe manner on their own pace. So how does that happen, right? We need to provide the infrastructure, provide the security policies, provide the automation to make that happen. We also need to keep in mind about separation of duties and what's developer responsibility versus what's secure. So once we enable that platform as a service, we move to the second graph. The developer responsibility reduces, and they can move faster and just focus. We want them focused only on their application code. Let developers develop, right? And then move more on the platform. However, as you can see, the bell curve here, in the initial build of the platform, there's a lot of effort involved in creating all the automation, creating this platform that developers can use seamlessly without involving security teams or platform teams. So it does end up being a little better, but obviously there's a bell curve in both directions. So, but what we're doing here is we're reducing the developers' upskilling efforts and reducing burnout. And then we're also eliminating all those complicated calls where platform security and developers all have to get on the same call and hash it out. So, and it happens more times than it's almost common rather than the exception, right? So, how can we fix this? So we can, on Google Cloud specifically, call that out, on Google Cloud specifically, There's two features that we can combine into one solution. One of them is Google Kubernetes Engine Gateway API, and then the second one is Private Service Connect, and I'll jump into those. So Kubernetes Gateway API. It sounds fancy. It's just the evolution of Ingress. So all of the features that we didn't like about Ingress, the developers around the Kubernetes ecosystem got together and built next generation of way to expose services outside of Kubernetes. Still the same thing, but it addresses all the original problems. So it has advanced traffic manipulation because it's built on the Envoy proxy, which is also built on top of Istio. So Istio has advanced inherent traffic management features, circuit breaking, traffic load balancing, visibility into the traffic. Just very nice complement to your services in Kubernetes. The focus here is not to talk about Istio, but it's built with Istio in mind, so it integrates very nice. So then as well, obviously the Ingress API, it's the legacy method. So you can see in the diagram here that when there was Ingress, you had the single file on the far left. The traffic would come in from the cloud, and there's the Ingress controller, and it would go to the services, and you had that argument over who owns that centralized object, right? With Gateway, we split that out, and we have the Gateway object, which can be segregated off to the platform or security team. And we're gonna kind of delve into that and why platform should own it. But platform would own that. And then the HTTP routes, where all of those traffic paths map to services, the developers can own, and we can lock that down on namespace so that the developers can manage their traffic and never have to talk to the platform or security team. And then on the other side of that, the platform team has their gateway object locked down to only accept traffic from the developers' HTTP routes. So it satisfies the platform requirements, as well as security is going to own, you'll find the PSC, which allows traffic to come in, so they can control if traffic is even going to hit the cluster. So everybody gets happy all of a sudden, and then we fix all of the problems that we originally talked about. I just wanted to call out, not to get too technical, but some protocols, right? I just had it as a footnote here, but the original Ingress only handles HTTP and HTTPS traffic. That's 80 and 443 on ports, which is pretty standard. However, the Ingress or the gateway is able to handle a lot more traffic patterns. It's all TCP ports. It can handle gRPC API, and it can handle TCP, UDP, in addition to HTTP, as well as TLS. So it's advanced, and I didn't want to go too much in depth, but just to mention that it's rich in features. So why, other than the rich features, why would we choose Gateway over Ingress? So and it's fair. This is a fair argument. Ingress has been the standard for the industry for years, and as you can see, the Gateway API on GKE only become generally available in October 2023. So that's recent in tech years. And it's important because when you go and you pitch these ideas to enterprises, they want to know these things. It's important for IT to standardize on something and not adopt latest and greatest just yet. We want tried and true. So also, Google has noted that they have their Ingress controller that runs on GKE, which is the Google Kubernetes engine. They've halted all development internally about new features on Ingress, and then they're putting 100% of their development effort on Gateway API on GKE because they see how important it is. So that's an extremely important reason to voice your concern when pitching this, that no new features will come out. And if there's some kind of bad feature or bug, you might have trouble getting it fixed. So important to know. I just mentioned about the feature rich, it supports the additional protocols. And then as well, a major topic that we'll be discussing here is the separation of duties. So, platform team, security team, and developers, and how this solution fits nicely into separation of duties, but yet allows a faster approach to deploying services. And then I also mentioned gateways built on top of Istio. So this is just reinforcing those points on a quick slide if you need to jump back to talk to somebody in the future about this. So part 2 of the solution, Private Service Connect. This is a Google proprietary feature, works on Google Cloud. It's similar to features on AWS and Azure, but they don't have the same name and they work a little bit different. So therefore it is proprietary. What is Private Service Connect? So if you have a service on Google and you would like to expose it to somewhere else in Google, and you want to do it privately, meaning private IP, RFC 1918 compliant inside your VPC, that could be problematic. So what are the 3 use cases, right? So it has Google APIs are public by default. So if you hit GKE, if you hit storage, if you hit BigQuery, you're going to the Google public IP address of that API to use that service. That's a problem for security. So traffic has to go outside to the internet and back to Google if you want to. So what can I do? I can expose Google service, take that, expose it privately inside my VPC with an RFC 1918 address. That's the simplistic model, right, for PSC. What I can also do, and I don't want to jump too far ahead because it's the next slide as well. I can take a service and build a new product inside my Google environment, and I can sell it to your Google environment and expose it the same way with a private IP address in your VPC. And we can be 2 separate entities as long as we're both on Google Cloud. And then the third use case being if I am a service in my organization, right? Just say I'm the database team, and I have 20 app teams that want to hit my database for some sort of query, right? I can expose that database to all those app teams inside their secure environments, right? So that's the third use case of PSC. That's the highlights here, looking through my notes. The other thing about if you want to know under the hood what's happening, as the traffic goes from left to right, and we call out here the consumer is anyone that wants to use the private service connect. The producer is who is creating the private service connect. But as you go across this into this secure link called private service connect, what's happening underneath the hood is a source NAT on IP traffic, a destination NAT on IP traffic, and a port NAT on the traffic, right? So it's taking each packet, completely transforming it so that, one, it can scale, right? If I have to worry about IP addressing and I'm selling this service to 100 customers on Google, and I'm customer number 1 and customer 2, and we all use 10 dot something. We all use the same IP address space in RFC 1918 land. We could have a problem on the producer side because we can't talk to each company and say, what IP address space are you using? Okay, let's not overlap. I won't use that. You won't use that. But then think about it at scale, right? There's 100 companies later. We've got a problem with IP address management. So therefore, it is inherently needing a NAT so that we can do IP addressing and not worry about either side's IP addressing, right? NAT's converting whatever you have to whatever I need it to be, and vice versa. So, and to do that, as you know, it's just like a Google internal load balancer. You've got to pick a NAT subnet. It's basically a pool of IP addresses that Google can use to, or the producer can use in this case, to expose that, right? Those are kind of the guts of it. And I know I didn't want to dip too technical, but I wanted to explain what was really happening there because it puts at least the network team at ease about how this is going to play. So best practice in this is to use a /29 if you're denoting some network space and you have to go talk to the network team about how am I going to do this? How am I going to expose services? And I need some IP address space. Some of these large enterprises that have 10 and 20,000, say, retail stores, you know who I'm talking about, they need to know this because IP address space is tight, especially if they keep it all internal. You can use that 10 dot and that 192 and the 172.16 pretty quick. And again, just putting some color to what we just talked about as far as the use cases. So you can see over here in the consumer side, we have the icon that looks like a microchip is a VM. So we're basically saying those are clients, right? And the clients request an IP address, a service, right? So this could be, an example would be an application talking to a database, right? So an application, a developer needs some sort of connection string to connect to the database at a low level. So what I can do is make that connection string point to one of these endpoints that's considered a PSC. And then Google Magic connects the PSC to one of three things, right? So it can connect to Google APIs, it can connect to third-party services, we'll call that, where I created a product and I'm selling it to you. And then also the last use case, like we said, it can be inside your organization. I'm the database and I'm trying to make my database available to 20 different app teams. So 3 good use cases. What we're focusing on today for this solution is the third in the bottom box here, the intra-org services. So that's me exposing my services to you as the developer, and we both work for the same company. Because this is what we've seen where the trend is, right? And specifically, if you want to see what that architecture would look like, if we take the third use case and then we zoom in to a 5,000 foot view from a 30,000 foot overview, we would have the clients, we would have a load balancer, where it says consumer load balancer. The load balancer backend would be a PSC endpoint. And then the private service connector is the Google Magic piece that connects, pipes it through. The service attachment is owned by the developer, and it would point directly to a GKE gateway load balancer. And so GKE gateway load balancers support connecting from service attachments. So you can see how the solution has kind of presented itself here by combining PSC with GKE gateway API. I now have a secure solution that allows 3 different teams to be involved and yet operate autonomously of one another. So, and when I say that, all of these components, they don't have to be built in order. If I'm a developer and I want to build my half first, fine. And if I'm a platform team and I want to build my, build the other half first, fine. We don't have to jump on a phone call. We don't have to spend time or slow anyone's efforts down. Everybody can function independently, as well as we can secure all these components independently to that specific team. If it's a security team, platform team, developer team, we can secure that as necessary. So I think this is basically what we're calling, but it's a bridge, right? In the previous diagram, the Google Magic part, the PSC connecting the consumer to the producer, we can call that a traffic bridge in terms of speaking from a management lens, as well as there's an inherent need here that this traffic can only go one way. And that's a beauty also of this solution. PSC is one-way traffic. So if I'm the producer side and I want to go out to the internet, I can't go through this link. So I've again secured my developers from making a bad mistake, right? They're going to have to go to another team or another method to get back to the internet. It can respond to traffic, obviously, but it's one-way traffic by default. Also, this solution appeases the security team because they don't have to upskill either. They can know that they have grasp of the traffic, obviously one way, but unless they enable that that PSC endpoint, nothing's happening, right? So they can own that that piece, and that's kind of the gate or the key to the castle, right? To get into the service, the security team has to enable their part, and they can do that at any time. So it's breaking those barriers where we're putting everybody in the correct group for separation of duties. So and what that last point here, if you just put it into terms, you're increasing the ability of your network operations and your security operations, right? So they call it NetOps and SecOps. Okay, this gets kind of complicated, but this is the entire solution put together and what it would look like to expose a service. So I'll jump into this. We'll start at the top of the diagram and then we'll go from left to right. But as you can see at the top of the diagram, we have our security team, and they can own what's in the box there. They can own the external load balancers. They can own the cloud armor. So the WAF basically is what that is in Google. It does DDoS, OWASP, all that stuff. So they can own the WAF. They can own the external load balancer, which is exposing traffic to the outside world. That makes them happy, as well as when they're ready, they can build the PSC endpoints for traffic, right? So security owns that piece. In the middle piece, the platform team, AKA infrastructure team, they're going to build the cluster, right? They're going to own the GKE cluster. They're going to build the namespaces. They're going to build the network policy to secure the namespaces. And then they're going to also build the service attachment, as well as they're going to own half of the gateway object. Or I guess they own the gateway object. They own half of the gateway. The HTTP routes will be owned by the developers. So we're segregating this into separation of duties, and as well as allowing teams to work independently and work fast. So going from left to right, there would be internet traffic, as well as you can do this for internal. We'll talk through that. But if traffic's coming in, it's going to hit Google's software-defined global load balancer. And again, this solution is standardized. So everything the security team does, it's cookie cutter. Everything the platform team does, it's cookie cutter. If they have one shared cluster or 10 clusters or cluster per app, we've even seen that. Or if the security team, right, it's one load balancer, multiple load balancers, it's still a template process. They take the code, swap out the variables, build another one. Nothing changes. We don't have to vet another solution. This solution fits every use case. So that it makes it nice from that standpoint, because we only have to figure this out once and then run, right? So also those load balancers, right? They need a backend in Google. The backend is the PSC. It's a form of PSC. It's called PSC NEG. That stands for Private Service Connect Network Endpoint Group. It's the same technology. It's a regional resource, balanced among local data centers. Still works the same exact way as PSC. It's just a form of it that can be a backend of a load balancer. Then still moving left from right, we have the Private Service Connect, which is the actual magic, and then the service attachment. The service attachment is basically a URL. It's a URL from Google that allows the PSC to point to the service attachment. Hey, I'm out in Google, and here's a URL. And it's not a URL that you can define. It'll be composed of region, project name, and some random alphanumeric characters. Then the gateway is standardized, and what we call this is gateway class. Gateway class, and I have a slide in the appendix to jump into the guts of gateway class, but there are basically 7 or 8 types of gateway classes, right? It's just a single line of code, but it says what type of load balancer does the gateway want to spin up. So in this particular solution, we're telling it to spin up an internal layer 7 HTTPS load balancer. And we're standardizing on that because the security portion or the external load balancer and the PSC neg is abstracting that away from the internal load balancer. So all traffic will be internal when it hits this because it's coming from the PSC. And then finally, the developers in their namespace, they can each have an HTTP route. The HTTP route can point back to the gateway. It can be secured in YAML to say only point to certain namespaces, as well as the gateway object can say only accept HTTP routes from certain namespaces. You can also put a network policy on top of that to secure it at the IP level, and then you can also use network policy to secure namespace to namespace. You can really dump some security on this. And then so the HTTP route would be packaged as a single file with all of the paths, and it would be packaged with the application code. So this is also scalable and future thinking. So Apogee, so that's a Google product. It sits outside the VPC in Google's VPC, and it is a API gateway. It's a Cadillac API gateway. It has all the bells and whistles that you could think of in an API gateway. This burns people because sometimes they build infrastructure first, and then they realize they need an API gateway once they start on their API evolution. And sometimes they have to rebuild and do like a network 2.0, rebuild a little bit of the network to support Apogee. This architecture supports it pre or post. I can put Apogee on day one when I build all this out, or I can put Apogee 2 years later after this is built out. It still is an easy plug and play into this architecture. And Apogee uses PSC. So how Google has already built their product is using the same technology that we're using for our solution. And just as a footnote on that, that we'll cover that in a minute. Let me keep going on this for a second. And there's a footnote on Google and PSC. So this also separates, as you can see, to different developer teams. What we call this and what can happen here, okay, is a variation, right? The DMZ, we can now call a floating DMZ because I can have one DMZ, one security point. This spoke VPC, I can make 100 of these and attach it back to the same DMZ. So the DMZ becomes a floating DMZ versus attached with a Palo neg. So I'm just jumping down in, right? I think we walked through this, but this is the scalability of it. We can have a prod and a QA and a dev. We can have as many environments as we want. It still scales out to this as far as the security view. And then jumping down into the platform view. And this is what I was talking about here, is that within this, there is a known issue where when you spin up a GKE gateway API, it spins up a VIP. That's a virtual IP address for the endpoint. It's of type shared. A service attachment cannot attach to a shared endpoint. It can only attach to a non-shared endpoint. So you have to create an additional VIP, which is just an IP address reservation, and attach your PSC to the VIP and then back into the forwarding rule. So you're going to end up with two IPs, and one of them is not going to be used. And Google knows about this, and they're working through fixing this issue. Just wanted to bring that up as far as, and then your developer view, they own the HTTP routes and they own the application code. So I just wanted to jump in real quick about highlights, right? So obviously this is all Google Cloud Native Services, managed services, the way you want to go in cloud, less you have to manage. It's a secure architecture with centralized controls. It's flexible. It supports API or Apogee integration before or after. It separates duties and improves your time for upskill. You've got a standardized architecture that you can copy and paste 100 times over, and it still works for whatever use case. And this equates to easy day two operations. Obviously, speed to market. I think we're good. I think we're good. Are there any questions? Okay. And so I know we're going to share these slides in the appendix. I put in there, the exact code you would need for your GKE gateway object with explanations, as well as your HTTP route object and how you would put that together if you were going to build that solution. So it's in the deck, and we'll share that out.